So good morning, I am Krishna Kumar. So we start with a new series of lectures on the topic of ordinary differential equations. So in this first lecture, we give a general introduction to what exactly is the theory of differential equations. Incidentally, this course is not about solving or finding the solutions of specific differential equations, which I take it for granted as the basic knowledge that is available for the people who are looking at these lectures. So something that is done at the undergraduate level, say specific techniques of solving equations is assumed. That's the background that I am assuming. Secondly, your knowledge of mathematical analysis is taken for granted to some extent, and you can see that many problems in analysis have had its roots in the theory of differential equations, because most of the theorems that you encounter in real analysis are supposed to have come up or supposed to be answers to the questions that came up in the study of differential equations. As we go on, I'll point out certain occasions where it is very visible. And then of course you prove a general theorem there, and then that general theorem goes into the what is called the toolbox of an analyst, and then it is taken at the right place at the right time and then made use of to draw conclusions. Anyway, that's how the subject is as such related to this. As such, differential equations came in the context of studying nature. The physicists, when they were formulating or looking at how things work in nature, they found that they eventually landed on the tools of calculus. Of course, as you are familiar with, Newton developed calculus in the context of solving dynamical problems, and he used it very extensively in his investigations on nature, which led to the Newton's laws and the various formulation of various ideas in physics, or expressing the laws of physics in terms of equations. So equations became a vehicle to express the various laws of physics. That's how the mathematical modeling came about of physical problems, and in this context differential equations came, and in the context of trying to find solutions of them, the mathematics had a spin-off effect, namely that lot of ideas developed there. So let us start with a physical problem. It's the motion of a single particle. So we assume that there is a particle of mass m units moving in a force field. For example, now you look at a feather leaf or a leaf dropped on the surface of a river. You know that there is a water flow. So there is some force field that is there because of the presence of water. And then you are dropping the leaf in that, and then it has no option, it has no alternative, and it has to take a certain course of movement. That it is carried away by the force field. Now this is something that is familiar to us. Another example is, in the gravitational field, suppose we throw a stone, then what happens? It takes a path and then eventually lands back. Because of the gravity, it is pulled back. So there is a path along which it travels, and it is dictated by the force field, that is the gravitational force that is acting, and also the initial velocity that you impart, and how you throw the stone decides on the trajectory of that, and from where you throw the stone and with what velocity you project it, it will determine the path of the projectile, which has no other no option to comply with these constraints. Now let us look at the equation governing this. So we denote by the vector r, which is instead of the conventional the x, y, z coordinates that we choose. So let me write it as x1, x2, x3 so that you can generalize very easily. Then we take the velocity v, the vector v, with the components v1, v2, v3, and then of course t is the time. So generally the position vector rt is given by x1t, x2t, x3t. Okay, so that describes the position of the particle. So the particle RT. So you have a time scale. You also have a sort of coordinate system with which you mark this. Therefore, RT is a function of x1t, scalar valued functions, x2t, x3. Now, what we mean by the particle moving in space is that the change of position of the particle with respect to time. So how the particle moves as time elapses. This is the question that you have. So say that at time t equal to t naught, suppose this is r t naught, then if it is moving along this path, then at a time t, this is at r. Okay. So we want to see what path it takes and relate it to the force that propels it. So what physics says is that there is a force field, and the second law of Newton's law, the second law of Newton says that the rate of change of momentum, is proportional to so once the particle is in a force field, there is a force acting on that at every instant, at every place. Okay. The force is in general, it depends on the space as well as time. That means then you are talking about a force field which changes with time. Or if you have a force field which does not depend on time, then it is determined by a function which is independent of time. So in general, this is what you have. F is a vector which depends on, in general, R, and you know that from your physics that dx dr by dt that's the relation between the velocity and the position. And t. And this has once again components F1, F2, F3, where F1, F2, F3 are scalar valued functions of x1, x2, x3, v1, v2, v3 and t. Okay. So what do we have? What is the scenario? The scenario is this. Suppose this is the space in which you are moving. Actually 3-dimensional. So what you have is that there is a vector associated with each point, and this is denoted by, this is F, which has components F1, F2, F3, and what you have is that you have a force field like this. This is described by F, and if it depends also on the time, then you see that this force field changes with time. It changes with space, it changes with time. So in general, it is a function of position, velocity and time that you have. Okay. And the Newton's law says, so there is something about the statement of a momentum. So what is the momentum? Momentum is essentially mass into velocity. This is what you call the momentum. And Newton's second law says that the rate of change of momentum with respect to time is proportional to the force field. I mean, this is proportional to, that means we have the equation some constant of proportionality times F, which is a function of R in there. This is a vector equation. Now I do want to avoid some complications, so we assume that the constant of proportionality is one. And we also take m to be equal to 1 unit, whatever be the unit that you prescribe. And in that case, what you end up with is m is a constant, therefore you end up with this equation. is the vector equation that you have to work with. The problem is this: given the force field, suppose you have a particle dropped in that force field, how the particle will move. So what is the path of the particle? In short, you have to find out what r is for the particle. Therefore, if you go for the scalar form of this equation, this is what you end up with: d2x1 by these are the scalar valued functions which are the components of R. They are unknown functions. Then and t is the independent variable. So we are studying everything with reference to a time frame. So as time elapses, where the particle would be found and what is the behavior of the particle, namely we want to know exactly how fast the particle is moving, in which direction it is moving, or in other words, we want to know the velocity of the particle. So we say that we know the particle. So this is the statement: we know the particle if at time t where the particle is, that means the position coordinates of the particle are known, as well as the velocity of the particle is known. In fact, there is a relation between the position of the particle and the velocity of the particle, namely that the components of the velocity are essentially dx1 by dt, dx2 by dt, dx3 by dt. Therefore, the problem is this: there is the variables, the unknowns are x1, x2, x3, where all these things are known here. f1 is given, and then you know that these relations are satisfied. I will also write the other two relations. This is the, I will write this way. And t. And so also for the to x2, x3, dx1 by dt, you know that here the unknowns are x1, x2, x3, and we want to determine them. And what is known is that the functions x1, x2, x3 satisfy this set of simultaneous equations. Okay? You cannot solve one equation in isolation in general, because what happens is x2, x3 are also involved in it. If you take the first equation, then x2, x3 are involved, their derivatives are also involved. In the second equation, x1, x3 are involved and their derivatives are involved. And third equation, x3, x2, third equation, x1, x2 is involved and their derivatives are also involved. So this is a sort of a system of equations, and they are all mixed up, and you can see how formidable is the task to find the solution of this equation. Let us see what do we mean by solution. I mean, we have to be have some clarity about this. Later on, I will be precisely defining what the solution is and so on, but at least to get a feeling for what it is. What we are looking for is there is some time interval in which you want to know the dynamics. In some time interval, you want to know where the particle is. This is a simple thing for each t. Okay, so we want to know what is for t belonging to some interval I. In other words, we want to find out functions x1, x2, x3 of the time variable t, which is the so-called independent variable, such that when substituted in this equation, these equations become an identity. Okay, so when you feed x1 here, the function x1 here, and compute the second derivative of that, you will get a function of t. And if you put f1 and substitute x1, x2, x3, dx1 by dt, dx2 by dt, dx3 by dt, and t becomes valid for every t belonging to I, and similarly for x2 for the second equation, and similarly for the third equation, so that when you feed these functions in these equations, they become satisfied. Okay, so that is roughly what you mean by finding the solution. So we are in search of functions of t, the independent variable, with the property that they satisfy these functions, satisfy the equation. So we have three simultaneous equations. It's not that one is independent of the other or any such thing. There may be some specific cases where this will happen. For instance, if you are working with one-dimensional motion, then there will be only one variable involved in the whole show. Okay, so if you are working with a two-dimensional motion, then you will have only two variables involved in it. So we will consider all sorts of situations like this. So this is generally, at the outset it's extremely difficult to find a solution. In fact, there are just a handful of equations which can be solved explicitly. That means, given the equation, you can find explicitly these are the functions which satisfy the equations. That is not in general possible. So given an arbitrary equation, it is not possible to write down the solutions of this equation. And what you can say is that what do you mean by writing down the solution of the equation? What is known is the function and the dependence of x1, x2, x3 expressed by the function f1, f2 and f3. So this is known. But the unfortunate thing is that the unknown function is involved in it. Therefore, these are also dependent on the unknown function, and we are searching for the unknown function. And you see that how difficult the problem could be. So even a simple problem like so let's come to, so here what we say is that even a simple problem could be quite formidable. For example, the simplest type of differential equation that you may encounter is, given a f of t, find a function x of t such that for t belonging to some interval I, such that in the case of certain elementary functions, we can explicitly write down the solution by integrating it. And what we know is that this is equal to f tau d tau, and the whole integration theory developed around this problem. So see, so if you look at this problem, is this, what is given is this function. It's not a complicated equation because here the function depends only on t, the independent variable, not on x. In that case, we see that this actually leads to the inverse problem of differentiation, namely finding out or integrating a function, the integral of a function. And integration theory is well developed. But still, you don't know, there are situations where you cannot really explicitly write down the solution in terms of the elementary functions. Now, what happens if the problem is something like this? Suppose your problem is something like this. A more general problem. A relation x and t is given f of xt what I would say is, rather than saying a relation, you should have some kind of equality there. A function of suppose we wish to find out a function x of t. We are taking t as the independent variable, x as the dependent variable, for t belonging to some interval such that dx by dt equal to f of xt. This is apparently a very simple differential equation. It involves only the first derivative, does not involve higher derivatives as you see here. Okay. But the problem is this: x is also involved in this function, not like this equation where you could write the solution in the form of an integral. But here x is also involved inside f, therefore it is more complicated. So this is actually an inverse problem. Okay, given f which depends on x and t in some way, find a function x such that dx by dt equal to f of xt, and that is what you call the solution of the differential equation. And many equations can be eventually formulated into this particular language by taking a more sophisticated form of it, namely going into vector valued equations. Now that I will I'll show you soon. Okay. So the question is how to find x for a function such that x is equal to gt for some t belonging to I and dgt by at t is equal to f of for every t belonging to some interval I. So the problem is just find out a function gt such that when x is replaced by the function gt, you end up with a function, and this is a function of t, this is also a function of t, and these two should be identical for every t or equal for every t. Okay, or this relation should become an identity in t. Then you say that G is a solution. But that is roughly the idea of the solution. I will make it more precise later. So you can see that even in this case, it is quite difficult to explicitly write down the solution of this. Okay. So one of the problems that you encounter is that most of the differential equations cannot be given a solution in the explicit form. Then what to do? In fact, this you can see it can be quite complicated. Depends on how these functions f1 and f2 and f3 look like. The whole problem may be extremely complicated to find a solution. But nevertheless, now you see that lot of information has been obtained on the behavior of the solution. Therefore, if you cannot solve this and write down the solution explicitly, then the next option that the mathematician provides the physicists with is to tell them, if your force field is of a certain type, then that property is reflected on the solution, or how the behavior of f determines the behavior of x, the solution. How the given function f here determines the behavior of the solution. So you may not know the solution explicitly, but you would try to extract as much information about the solution as possible and relate it to the properties of the given f. And that's a way of attacking the problem. And this is what you see in differential equations. And the entire theory is developed to address this problem in this language. So one of the questions that you ask is this. First of all, if you can solve it explicitly, what do I mean by explicitly? Finding a GT here such that when you feed this GT in the place of x, this becomes an identity. So if you can solve explicitly, then everything is clear. You just look at the properties of G. But that is not often possible. Okay? Therefore, you just cannot see the solution explicitly. In that case, what do? Indirectly, can you see the solution? this one. Indirectly, this is the problem that you have. Okay? That means extracting as much information about the solution as possible from the knowledge of the nature of the differential equation. This is the problem, and that is a problem that mathematical analysis had been addressing all along. So one of the basic questions that comes is this: given differential equation, first of all, does there exist a solution at all? Or in other words, the question is, given the differential equation, say this one, I am keeping it as a prototype for very valid reasons. Later you will see that this study of this is for developing a theory. This first order equation or its analog of first order systems would serve the purpose. Okay. Given the differential equation, does there exist, does there exist an interval I such that for every t belonging to t, I, a solution exists for the problem? Namely, there exists a function xt defined on the interval I such that dx by dt, dxt by dt this is what we are looking for. So if you cannot explicitly find the function, still is there any way in which you can assert that there exists such a function? You may not be able to express it explicitly, but still you are sure that a typical result of this kind would be that if f satisfied a set of conditions, then there exists a time interval on which the solution exists. A typical result would be if a set of conditions, then there exists an interval I and a function xt t belonging to I such that this is a typical existence theorem. The second question that you ask is the following: is the solution unique? So, before I talk about the uniqueness problem, let me go back to the equations of dynamics coming out of the second law of motion and try to see what it is. Physically, you will know something, and mathematically, what they mean, what we mean by that. The equation that we are looking at, I will write in the vector form since you are already familiar with the notation. This is dr or d2r by dt square equal to, this is a vector, for a given function f. I will make it more explicit and clear later. Now we are asking for a function which satisfies a function r of t, vector valued function r of t, which when substituted will make this an identity over some interval I. So let us work on that. Now let us look at the physical problem. The physical problem is, for instance, let us take a very natural problem that we are familiar with, and you would have also done this probably in your physics. It's the problem of throwing a stone. Well, we live in the gravitational field. Okay, so you have got the gravitational forces acting like this. Which fortunately is constant everywhere, at least in a small neighborhood of the earth. Okay, but directed towards the earth. And you also do all sorts of approximation that at least locally the surface is flat. Okay, and then the problem is, see, at some point, from some point, at some particular time, you are projecting a particle, like throwing a stone. There are two things here. One, the position r0. Okay. The second thing that you have is, so at time t equal to t0, r t0 equal to r0. This is the initial position. Suppose you allow the particle to be at that place at time t equal to t0, then the path, it takes a particular path depending on what velocity if you allow to drop or something like that. But now at the same time you throw the stone. When you throw the stone, you are imparting a certain velocity, and assume the velocity is v0. v0 is the initial velocity. Then what happens? You would have seen that the particle would take a parabolic trajectory. Okay? And you see that the path is tangential to the velocity the initial velocity at that point, and at every point the velocity is given by is in the tangential position. Now suppose you were to throw this, change the initial velocity, something like this, then what happens? The path taken will be something like this. So you are interested to know where the particle is after you launch it, especially probably at a specific point where it hits earth again. Okay, because your purpose of throwing the stone or sending out a missile is to drop it at a particular point at a particular time, whether that is achieved. So you see that once you launch it, once you fix the initial position and the initial velocity, then you have no control over it, unless you have some mechanism to change this force. If it is in the gravitational force, then it travels. Okay, it starts from there and then it follows the path, it goes up to some level and its momentum expires and then changes direction and the particle will start descending down. It ascends to a height and then descends it. And what you have proved mathematically is, maybe it is worthwhile for you to once again go through that. The path of the projectile is a parabola. So it follows a parabolic. That's a law of nature. So that we have found out, and you can explicitly find out the path of the particle once you have the initial parameters. And there is only one path along which it goes. And that one path depends on two things, namely the initial position as well as the initial velocity. Therefore, the initial position and the initial velocity act as conditions, as the initial . So you are often the physical problem is this: you want your projectile to hit a target at a particular time at a particular point. Then the question is, with what, from where, or you have an initial position from where you launch, so that is fixed, say, that is R0 is fixed. So you can manipulate the initial velocity. So you have to compute the initial velocity so that you hit the target at the right time. So that's the problem. So once you know the general problem is solved, then from that you can make the computations required and decide on the initial position so that you can plan your launch of the missile or stone. Okay, that's it. So there is something called the initial condition. So when you change the initial position as well as the initial velocity, in this case the path also changes. Now incidentally, d2r by dt square is the acceleration, the rate of change of velocity that you have. Of course, I started with the momentum. In fact, I have assumed that the mass of the unit of the particle is 1 unit, and assuming that this is the nature of the equation, otherwise I can pull the mass into this function and there is no difficulty. So it's something like this. So the relation between the velocity and the force is given. That comes from the Newton's law, and this is not something mathematically derived or anything. This is a physical observation and physical hypothesis, and mathematics or the calculus has been developed to you know, express the various things like how to find the position, how to find the velocity, or how to express the velocity, how to express the acceleration, and how they are related to one another is also a part of the physical laws. Okay? They have evolved out of observations and experimental data, and that's how physics works. And once that the whole equation is handed over to you, to the mathematicians on a silver plate, and then you have to ask the right questions, find the right solution. Therefore, you see that given the equation as it is, there are several solutions possible for this problem. Okay? I will just give a very simple problem. So again, let me go back to the river. So there is the river flow of the river. Now I assume that it's not a time when there is a turbulent flow or any such thing. That means it's a steady flow that you have. And therefore what you have is, there is a velocity field. You look at the surface of the river, there is a velocity field. At each point there is a direction in which, I am also assuming that this does not change with time. Certainly in a turbulent flow, say something like a rainy season, there's a water rushing and every moment this will change. But I am assuming that it's in a sort of rather calm and quiet season the river is flowing, and where the flow lines do not change with time. Okay? Flow lines come out from this. So now let me see what the flow lines are. We will look at this. What you have is that, suppose I drop a leaf here, then what happens? There is a velocity field that you have there. So the leaf would start following that track, and then at each instant there is a new velocity coming up, and then so it takes a path. And what you know is that at each point, okay, there is a velocity acting along the tangential direction of the path. Therefore what you have, starting from the initial position, there is a path the leaf would follow. The path of these leaves is what you call the flow lines. And the property is that the flow lines, their tangent to the flow lines give you what is called the velocity at that point of the flow, and the leaf would follow that path. So what I wanted to say is that it depends on where you drop the leaf initially. At time t equal to t naught, then it will follow a path. So that's the solution. If you drop it at another point, then it will be another solution. If you drop it at a third point, it will give you another path, and it's another solution, and so on. So there are all these flow lines correspond to what are called feasible solutions of the problem, of the differential equation governing it. What is the differential equation governing it? It is this, that is dr by dt. Yeah. What is given is VRT, and I have assumed that this does not depend on t. Therefore, it depends only on position. Therefore, what do you have? I have dx1 by dt or dxi by dt equal to v I x1 x3 for I equal to 1, 2, 3. What do you have? You have three variables, three unknowns x1, x2, x3, which are in general functions of t, and there is a function of this prescribed which will give you the velocity field, and in that velocity field you are dropping a particle at some point and it takes a path, and that path is what you call the flow line corresponding to that. So through each point you have a flow line. Okay, there are a lot of questions that immediately come up. Okay, so it makes it very clear that there is no single solution for this, but there are many solutions for this. Now, what does it tell you? Can you isolate a solution from it? One solution from it? Yes, you can do that, provided you fix on the point where you drop the particle. So, suppose you have xit equal to xi naught. That means there is an initial point r naught given by x1 naught, x2 naught, x3 naught. Then you have to solve this system of equations with the initial data, that xit equal to xi at time t equal to t naught, that is the initial time, equal to xi naught. So you are starting from the point, from the at the time t naught, from the point r naught, and then you are asking where you would reach at time t. Okay, subject to the flow that is there in the river. So you will follow a particular path, and then that path will describe the position of the particle at time t, satisfying the initial condition, namely that r naught equal to x1 naught, x2 naught, x3 naught. Okay. Well, natural question is this there is only one path, or suppose you start from here, is it that you will go like this, or like this? This is the question that you ask. Your gut feeling tells you that as soon as you are here, there is only one direction in you are pulled. Okay, it's all initial inferences. Only one direction you are pulled, and therefore you would follow a path, or what you would expect is that fixing the initial position fixes up the path of the particle. In the case of a more general problem like this, you will see that coming from the Newton's law, this is coming from the relation between velocity and the position. You will see that initially fixing the position as well as the initial velocity will give you a unique path. Okay, so out of the many solutions that you have, you can isolate solutions by fixing the initial position and initial velocity in this case, whereas in this case just the initial position. So this talks about further conditions to get a uniqueness. So one of the second question that you ask here is, this problem is actually quite complicated. Yes, you are going to see when we try to address this problem, you will see a lot of new things start emerging, new demands start cropping up and so on. But I am trying to link it up with a realistic position. Okay, what is the third position? Now you know that when you solve a differential equation, as I said explicitly, writing down the solutions is nearly impossible except in a very few handful of cases. Therefore, the method that usually the physicists and engineers employ is to work out some approximation technique. Okay, so you have the concept of what is called approximate solution. Okay, now you will see that in the physical world this is nearly built into the problem itself. Why? Because first of all, the force field has to be known, or the velocity field has to be known in the problem, and that is an approximation to the reality. Okay, right? When you formulate the problem, you have to give this F here or V here, and that is an approximation, and it comes out of measurements. Okay. The second problem is this. As I said, there is an initial data. What is the initial data? You have to say where the particle is at time t equal to t naught, at some t naught. Even the measurement of time itself can be done not accurately but approximately with a small error, because there are limitations for your techniques. And then even the position, depending on what instrument that you use, there is a error in the position that you measure. Therefore, strictly speaking, you will be solving an approximate problem to the reality, be slightly deviated from the reality. So all these functions, the force function or the velocity function or the initial position or the initial measurement time, all these are going to be approximately done, given. For example, if you want to launch a satellite, okay, then what will happen? You will be fixing the initial velocity, you will be fixing the initial launch parameters, and they are all approximate to what you really achieve. Okay, what you assure is that the error that is involved in fixing the initial conditions is small. Then the field into which you are launching the whole thing is also not exactly known but only approximately known. Okay, therefore what you have is that approximate values of all the things involved, and then you are solving it. And then apart from that, you have the problem of solving it exactly. Whatever is available, can you solve it exactly? And that's also not possible. So you use some techniques, approximation techniques of various types to solve this problem, and numerical analysis is developed with this objective. Okay, then what is your concern here? Your concern is this. Suppose you make a small error in the initially. Will the error blow up with time? So that the prediction that you can make using the solution is useless if it blows up. If it doesn't blow up, then the solution that you use is useful. It also tells you, so you want to find a relation between the error in the solution at time t with the error that you can make initially. Okay? Right? If this error is established, then you see that you can allow a certain amount of error in the solution, in the physical problem. So to reach out that how much error you can have or afford to have initially is a problem. Okay, so this relation between the error that you make and the the consequential error that you have is a part of the information that you require. Okay, so finding out how depends on the data. Relate the solution to the initial data, or which amounts to saying, suppose you make an error, what is the corresponding error that you can predict with respect to which, or what is the accuracy with which you can make the prediction, so that you can control the error in the initially, so that the achievement that you expect is realized. Now this is one of the problems that you have. Okay, I will give an example, then it will be clear. There are two problems fused into one. Okay. One is the population growth problem. The model that I am giving is not the accurate one, though, but it's some model. Make an assumption that the population at a given time t is proportional to the growth of the population is proportional to the existing population. It's a very simple elementary model which is far from reality. So what you have is this: suppose xt is the population at time t, then you are asking this d by dt of this is proportional to xt, or what you have is this dx by dt equal to k times x. This is the equation that you have to solve. See, this equation also represents another problem, namely what is called the sort of radioactive decay. So this is population growth problem. So also you have the same equation, what is called the radioactive decay problem, where of course here K is taken to be positive, here K is negative. So if you have a radioactive material, if you leave it, what happens is, as time elapses, it will decrease through the process of what is called radioactive decay. And what happens is, the rate at which the quantity decreases is proportional to the actual quantity available at a time, and it can be, it's a very simplistic equation, namely dx by dt is equal to kx, where k is negative because it is decreasing. Here it is increasing, therefore k is positive. In both these cases, you see that the solution is something like this. Xt equal, it's a very simple equation to solve. X at t naught into e to the power k. This is the solution. T greater than t. So that you have x t naught is equal to, let me write this x naught. X naught is the initial quantity that you have. This is the population at time t equal to t naught, and this corresponds to the population of the radioactive material at time t equal to t naught. So this is the solution of the problem, and that's a simple differential equation to solve it. Okay, what happens? When k is positive, okay, now if you try to plot the graph of this is the time interval, okay, this is x quantity that you have. So at time t equal to t naught, the quantity is some x naught. So you are starting from t naught, x naught is the position. And then you see that if you plot the graph of this, it is going to be something like this in the first case. So what happens, suppose I make an error initially. Suppose I make an error initially, that means at time t equal to t naught, I compute the x naught with an error. What happens in the population growth problem? There is an exponential growth, and that error gets magnified, so that your model is not good enough to make predictions with a certain accuracy unless you are very accurate at the initial position. Okay? Small errors will just magnify through the system. On the other hand, if you look at the population or the radioactive decay problem, then you see that what is the nature of the solution? The nature of the solution is it starts from here, and then it as t goes to infinity, it's going to 0. Just go down like this. Okay, this is the radioactive decay. So this is the case for k negative positive. Okay, so starting from x naught, it will just start decreasing, goes to 0. So even if you make a small error, what is going to happen? The path will be eventually getting closer and closer. Okay, so initially you can be a bit careless with the measurement of the quantity, but after a time, if you want to measure it, it's going to be the same. Whereas in the population growth problem, whatever small error that you make initially is going to magnify the quantity that you have. Okay, so a relation between the error in the solution and the error in the initial data is something called for. Apart from that, there are other error factors which bring into errors. So how the solutions depend on the data? This is one of the questions that you have. I think I have made it amply clear what exactly it is in these two examples. Now another problem is more mathematical. It's called what is called regularity problem. Okay. I think I am going to stop in another 10 minutes time and then take it up in my next lecture. Let me call what is regularity problem. This essentially stands for the following. Suppose there is a certain amount of smoothness for the function f. Its dependence on the variables here. Okay, or more generally on f1, f2, f3. Its dependence on the variables involved. How much of that is inherited by the solution? Or essentially you are asking a question about how the smoothness of the solutions are related to the smoothness of the solutions, of the initial data. How do the solutions depend on the initial data? Or what is it's not the same thing as this. What I am saying is that how the smoothness For instance, you know that suppose this function is a C infinity function. Can you say the solution is also a C infinity function? Okay. Or suppose it is a C1 function. How much of smoothness you can expect for the solution? Now these are some of the questions which is bundled into one class, namely the regularity problems. The next problem that you come up is what is called stability problem. Stability problems are essentially the following. Suppose you initially start somewhere in the neighborhood of the initial data. Will the solution stay? Will that corresponding solution would also stay in the neighborhood of the solution for all t? Okay, or for some t, or how far it will stay near this solution. These are the so-called stability problems. So these are some of the general questions that we are going to address in this course of lectures, and the various tools required for that. And what I plan to do is to follow the MIT course, namely not the current MIT course, the course given by Hurevich several years back, but still very relevant. And then ask these questions, in which you will see a lot of analysis will get developed during this process. So many of the things that you learn in analysis will become very handy to understand these problems. So this is a very general introduction to this. Later on you will see that you will get your own insight into the problems, and how you tackle with them will be visible as we go on. So thank you very much, and I think I'll stop here.